This is my presentation for CS358, Neutron Parallel Computing, my final project. I decided to do a parallel pixel morphing project, and I'll explain what that is in more detail. And before I explain like the algorithm and like the actual math behind everything, the general idea was actually inspired by an Instagram reel I saw, where someone uploaded a picture of a piece of bread, and then pixel by pixel, it transformed into a picture of Obama. I think it was pretty funny. And I was like, okay, I wonder what the algorithm that creates that is. And I researched into it, and it's actually something that I thought was, very easily parallel, or okay, which at the first glance seems very easily parallelizable. But in reality, it's way more complex than I expected. And I'm excited to teach you guys what I kind of learned in this project. Before we go through the rest of the presentation, I think it's going to be super useful if we look at a demo. Very briefly, I created a Streamlit application that runs like my two other scripts, but specifically like these two scripts can be run by a terminal, but then the Streamlit application helps visualize everything. So if I go to my Safari, you can see that this is like the Streamlit application, and I can drag and drop essentially two PNG files. So let me start with a piece of bread, and then I'll start putting in a picture of the lava. And there's a bunch of settings here, but essentially the first thing that's going to happen is essentially we've resized the images to be the same size, specifically 256 by 256 pixels each. Then we essentially sample different pixels of the image. So you can see the different samples of the image just to get the 256 by 256 grid. Then we're essentially getting like an importance of different pixels throughout the images. This will make more sense as I explain how everything works, but you can see the images are 256 by 256 cropped now. Now we can split into different hue segments. Essentially, again, this will make more sense when I explain how the algorithm works, but we're fundamentally splitting off each segment or each color index into different segments for different hues across the 8 different cores that I have on my computer. And then we essentially are running like a greedy algorithm on this to figure out where the first choice conflicts are. And then once we review this, we can essentially see that there's 8 jobs and 12,000 different combinations that happen. Right. So now if I run the full script with all these settings I explained, it's going to take a couple seconds, but you see that it's running parallel. And obviously, sequential would take way longer. It would take significantly longer. And I have some results at the end of my presentation that describe how long a sequential versus parallel of this would take. But you can see this like the terminal output, and you can see the final GIF that it outputted here. Sorry, it's like a little bit too small. But as you can see, each pixel by pixel of the bread image is now being rearranged into its optimal position for the Obama image. Pretty cool. So now let's think about how did this work? How does this happen? So let's go back to the presentation and let's talk about that. So, all right. So as you can see, that's kind of what the output is. So let's talk about how this is a very complex algorithm that I didn't expect to happen. So overall, the first problem, right, is that we essentially need a bijection between the two, between each pixel of the two images, right? So let me skip ahead a little bit first. Actually, I think that'll be more easy to visualize. So let's say in this example over here, we've got this image called X, and we've got the second image called Y, right? In this example, source X is the image that we uploaded. So in the example I showed you before, this is like the bread, and target Y is this destination image. So for example, the picture of Obama. You've got pixels such as X0, X1, X2, and so on. And then you've got Y1, Y0, Y1, Y2, and so on. Basically, the way it works is we're trying to figure out what is the optimal pairing from each individual X0 into the Y0, or into the Y target, right? So, for example, let me go back to like our original, the previous slides. Basically, what's happening is we are taking, let me simplify the example a little bit. Let's say you have some image X, so this is the original image, and some target image Y, which is also 2 by 2 pixels. We're trying to figure out the optimal place for this pixel to go in order to best create image Y, if that makes any sense. And so this algorithm, the way it works is, let's say this is like this is a fully orange pixel. This one is like slightly less orange. This one has only a little bit of orange, and this one has no orange. Basically, what we're doing is, or okay, and sorry, and over here, we start off with the fully orange pixel here, slightly less orange here, the like one stripe of orange here, and then no orange in this top left corner. Basically, if we run the algorithm, what we're trying to do is we want to pair each one of the most orange pixels with the most orange pixels. right? And as you can see, the easiest way to do that is by finding the Euclidean distance of the RGB codes. As you might know, RGB is stored as a XYZ value, which has inputs for the red, green, and blue, you know, um, integers that define that color on a spectrum. Using that, we can create this Euclidean distance, and finding the absolute or the magnitude of that distance gives us a distance value between each one of the y pixels and each one of the x pixels. Basically, for each one of these y pixels, we will calculate how far is each one of the individual x color pixels. So let me explain what that means, right? So for example, let's say we have some pixel, y1. So let's say that's the first pixel in here. We'll calculate the distance from, for example, x1, this x2, x3, x4, right? And again, this is using the RGB formula. And let's say, this becomes some double value, some floating point. Let's just say this distance is 1, this distance is 2, this distance is like 3, and this distance is 0, right? Again, this is just hypothetical. But fundamentally, what will happen then is that we sort within this XY configuration, and we see that x4 has the smallest value. And so then y1's first pick will be x4, second pick is going to be x1, third pick is going to be x2, and then final pick is x3 because that's the most efficient solution. What'll happen then is then we'll go to the next pixel and then figure out what that pixel's ranking is and essentially assign pixels in that way. So that's a greedy algorithm. The traditional solution to this is brute forcing, which is a O of n squared solution, which takes a long time. Rather, by using this greedy algorithm, I was able to simplify this solution. So now that you have a brief overview, sorry, that took a little bit, we can now talk about the more specific way that this greedy algorithm is implemented. So there's two main data structures that I use for this, right? Basically, as you can see, there's two main things we have to do. First of all, we have to go and find the distance between each of the x pixels from each of the y pixels. And then for each y pixel, we have to go down the list and essentially figure out which x pairing should be given to that y pixel, right? So we need two things for that. First of all, we need to figure out the order in which we go down the y pixels, right? So again, let's say we have some target image y, and we have a 2x2 matrix within the y pixel, or within the y image. We don't necessarily want to just go from pixel 1, pixel 2, pixel 3, pixel 4, because this is going to get rid of the heuristic that determines whether each pixel has, like, it's going to get rid of the optimal pair. Instead, what we want to do is figure out which pixel is most important, right? Let's say that this is the most important pixel, then this is the one that should pick first and get priority over, for example, this pixel, which might be less important. So because of that, we compute this statistic called the importance order. Basically, what this is saying is if given pixel y is more important than some other given pixel y, that gets to select first. Because again, we can only pick one x for each y. Again, this might not make much sense right now, but once I walk through an example, it'll make more sense. I think the equation's written here just as like in case you're interested, but the equation itself doesn't matter too much. But fundamentally, we're computing a score y to rank each y pixel. Then for each y, we build a rank of that y as a selection order. And we find the distance, RGB distance to each x pixel from each y pixel. So again, that's very high level theory. So let's talk about how that might work in practice. Here's a pseudocode if that's how you might interpret better. I won't walk through this just for the sake of for the sake of time. So let's talk about the more visible solution. Over here, again, like I talked about this slide a little bit, but you've got the source X and source Y, right? And you have a 3x3 image on both ends. Basically, we've got 9 pixels and we want to find the same source. Let me first begin by explaining the sequential solution to the problem, right? The sequential way is, first of all, let's say that you've got this. You can see that source X is now a little bit dimmed, right? So now you've got just like regular green pixels, red pixels, and so on. What's going to happen first is the algorithm's actually going to start at target Y, right? And it's going to say, all right, what is the most important Y pixel? Let's say that, and again, the way we pick that is by a couple of categories such as centricity, such as the hue, stuff like that. I won't get into that for the sake of time, but let's just say we assume that Y4 is the most important pixel because it's the sender one, it's the brightest, it draws the most attention. So this is the one that gets to pick first. Well then, Y4 will then rank each of the X pixels, right? Let's say it says that X6 is its top choice pixel, and then X4 is next, and so on. It'll rank every single X1. Again, for the sake of time, I won't list it all out, but let's say, it ranks X6 and X4, and then so on, right? Then, we'll finish ranking every single Y target pixel. For the sake of example, let's just say Y6 gets to pick next. Y6 would then be allowed to pick their own pairs. And notice how Y6 is also a green pixel. And so Y6 might pick X6 and then X4. But notice that in this case, Y4 is given X6 because it's the first priority. Even though Y6 also has the same picking order of X6 prioritized to X4. So since this is a clash, Y6 is allowed to essentially Y6 is not given X6. Instead, it's crossed out, and X4 is given the solution. That makes sense.
You want me to
So
take
this
a
is how the sequential solution would work, but the parallel solution is a little bit different because it seems trivial, right? You could just divide this target Y into segments, but that's not possible, and I'll explain why. So let's say we divide this into 3 threads, assuming we have like 3 cores, right? Then each thread would run at the same time. Well, now instead of going sequentially by Y4 and then Y6 and so on, what's going to happen is you see a weird solution. Basically, if we run this, both Y4 and Y6 point to X6 as their first choice. But the issue is the program crashes, right? Y4 and Y6 can't both get X6 as their first choice. But since it's running sequential, or since it's running in this parallel arbitrary form, it's going to crash since both are assigned. This is the first possible crash the program can have. The second possible way the program can fail is actually even worse. Let's say Y4 and Y6 both go, and instead of a race condition, the program assigns them both X6, and you can see the smiley faces have now appeared. This means that both of them are now allowed to have X6, which is going to lead to a big problem. Essentially, the program is going to assign both Y4 and Y6 the X6 pixel. And that means that once we actually draw the final result, X6 is going to try to go to both and interpolate between both. And then X4 in this example is not going to be assigned anything. And so you'll have an empty picture with like corrupted pixels and missing pixels. So as you can see, trivial parallelization is not easy for this problem. My solution was a more unique parallelization solution, right? So clearly we need a better solution to parallelize than simply dividing the pixels. And the solution is to group pixels together to reduce the overlap. So intuitively, 2 green pixels are more likely to match to the same pixels. So running these in the same thread is going to reduce collisions. Like in this example, the reason why Y4 and Y6 collided is because they were the same color. And so they both had the same preference ordering of X6 and F4 or X4. However, if Y6 and Y4 were in the same thread, then Y4 would be forced to run before Y6, meaning that even if they collided, our algorithm can account for that and properly keep the bijection heuristic. So basically, here's what we did. Here's the pixel grouping algorithm. We're essentially assigning pixels in order of importance, which is what I explained earlier. And then this is the greedy assignment through conflicts. But now here's the way we parallelize, right? Essentially, we split by hues. So hue 0 to 120, right? Let's say that this is a green, right? Hue 120 to 140 is red, and hue 240, or sorry, red, green, blue, right? So what this means is in this case, for example, right? If assuming we have 3 threads, which we can have as many workers as we theoretically can have, right? Any pixel that is hue 0 to 120 is going to go inside this thread. Any pixel that has hue of 120 to 240 is going to go in this thread, and any pixel that has a hue of 240 to 360 is going to go in this thread. Because of this, it's going to reduce conflicts, and then now we can run parallelization with the local KNN and the greedy algorithm. And then finally, we do a merge and global repair. And we obviously will have a couple of duplicates because we can't perfectly guarantee edge cases for 120s, for example. But we can reduce the duplicates because there'll be way less of them and fix the algorithm for those and guarantee the bijection as well as similarity to the sequential algorithm. So in general, why do we want a hue, right? You might be wondering, why am I using hue as like the split, right? Well, pixels with similar hues tend to match within the same color neighborhood, right? So by sorting particles by hue and then splitting into these segments, we can reduce the amount of cross-segment contention there is, right? So again, in our example, we had the two greens. If they're put into the same thread, then they won't clash. But if they were in different threads, there's a possibility of them having the same preference ordering. The parallel stage then segments these jobs to the workers, and then each worker computes local matches in its segment. And the main process is going to segment the matches and then repair any conflicts. In terms of like how the parallelism works, you could see that instead of having the four segments done sequentially, you can do them at the same time across different hues for four cores, for example. And then finally, you only have one big synchronization point at the end, which makes everything really clear and easy. And then, in terms of the correctness, right, we have to make sure the bijection is guaranteed. At a very high level, we just repair by combining the pixel threads. And if there's any collisions or reused pixels, we assign a contrast of the pixel between both. Finally, just the visual results, you could see that the sequential and the parallel solution, these are like the earliest frame, middle frame, and the end frame for like both the sequential and parallel view. You could see that, the pixel is, it's essentially the same, it's like the same exact thing, right? So it's clear that the sequential and parallel version are running in the same way. And we also employ some alpha blending at the final. I also decided to use alpha blending at the final stage in order to make the bread image look a little bit more like Obama, which is, just a fun addition. But yeah, finally, in terms of performance, I'll talk a little bit about Amdahl's law and the overhead that this might bring. So in terms of the measured speedup, you can see this graph. There was a speedup of 2.29 x for parallel versus sequential across jobs. So it was effectively linear, and it had like a 57.2% efficiency, is what I calculated. However, the max speedup of like this 2.29 is limited, right? Because you can see that this is what the timing is broken down by. The rendering was what I was able to get down. Or you can see the rendering and the save is like relatively equal for both, right? But the main place where you can see the save in time is like in the total sphere, right? What that means is basically by cutting down the sequential um, overhead from being done one at a time, we're able to get rid of around half the speed, which is pretty good, right? But the issue is with Amdahl's law, we know that we can't get, you know, speed up past a certain point because of the overhead that comes with the matching each pixel, figuring out the RGB distance and stuff like that. And so it becomes difficult to actually have it. In terms of the scaling curve of speed up versus efficiency, this is like a brief, quick scaling curve that I was able to calculate. You can see that as you have more jobs, you see like diminishing marginal returns, econ concept there. But as you get to like four or more threads, the net decrease you get isn't perfectly linear because of the overhead you get with the additional RGB calculations we have to do. Finally, in terms of Amdahl's law, not everything is parallelized, right? We have like the image IO, some pre-processing, stuff like that. There's also load imbalances. In terms of how to improve, better load balancing and vectorization could help with the computation itself. And so that's what next steps would be if I were to do this again. So yeah, with that, this brings us to the live demo stage, which we already talked about. But the main thing I want to explain now is essentially walking through everything one more time. You could see that the first stage was like resizing the image, then sampling some of the pixels to see like where they would end up. Then now, as I explained, you could see the importance. So essentially, we're figuring out the importance by looking at the luminescence, the importance of certain pixels and edges within the pixels themselves, within the image themselves. And so, for example, these images, like on Obama's collar and head, are the ones that are going to be targeted the most and most important because across all three spheres. And that's how we do the Y preference ordering. And the hue split into the different segments that we have. So you can see the hue is sorted across these different segments. And then you can see some candidate runs of the hues. And then finally, you could see like the greedy algorithm. This is how it's going to work. And then if I were to run the full thing one more time, it takes a couple seconds, maybe around like 10 to 15, as I ran before. And you can see how this is going to work in real time. Give it just a couple more seconds. It should show up. Here we go. Here's the full run. And one more time, you can now see how the pixels all correctly transform from the bread into the Obama shape. And yeah, that is my presentation. Thank you for watching.